Hey everyone, in previous lecture I already discussed how to identify linear homogeneous recurrence relation with constant coefficient. In today's lecture I will discuss how we can solve linear homogeneous recurrence relation with constant coefficient. So basic approaches will compare an with r power n. We have the recurrence relation an equals to c1 an minus 1 plus c2 an minus 2 plus till ck an minus k. This recurrence relation is linear homogeneous with degree k, and a power n equals to r power n if and only if r power n equals to c1 r power n minus 1 plus c2 r power n minus 2 plus till ck r power n minus k. So an will be equals to r power n if in place of a n minus 1 we'll write r power n minus 1, in place of a n minus 2 we'll write r power n minus 2, in place of a n minus k we'll write r power n minus k. Then a n will be equals to r power n. Now divide both sides with r power n minus k. N minus n plus k. So n minus n will be cancelled. R power k equals to c1 r power n minus 1 minus n plus k. So n will be cancelled. K minus 1, right? R power k minus 1 plus c2 r power k minus 2, like this ck, because this r power n minus k will divide with this. Now this thing we can take to left side. So r power k minus c1 r power k minus 1 minus c2 r power k minus 2 till minus ck equals to 0. And this is our characteristic equation. So by dividing both sides and taking the right side into left side, we got this characteristic equation. R power k minus c1 r power k minus 1 minus c2 r power k minus 2 till ck minus 1 r minus ck equals to 0. This is our characteristic equation, and the solution of this called as characteristic roots of the characteristic equation. Now theorem 1, let c1 and c2 be two real numbers. Suppose r square minus c1r minus c2 equals to 0 has two distinct roots r1 and r2. So here in place of k we are taking 2. R power 2 minus c1 r power 1 minus c2 equals to 0. Then the sequence an is a solution of the recurrence relation an equals to c1 an minus 1 plus c2 an minus 2 if and only if an equals to alpha 1 r1 power n plus alpha 2 r2 power n for n value 0, 1, 2 like this, where alpha 1 and alpha 2 are constant. So we have two constants c1, c2. We have the characteristic equation and characteristic root. Now an will be the solution if an equals to alpha 1 r1 power n plus alpha 2 r2 power n. Okay, and here alpha 1 and alpha 2 are the constants. Let's see one example that you can understand. Example 8. What is the solution of the recurrence relation an equals to an minus 1 plus 2 an minus 2 with a0 equals to 2, a1 equals to 7. So here recurrence relation is given, characteristic equation is not given. First we need to write the characteristic equation, right? So for this we can write r power n equals to r power n minus 1 plus 2 r power n minus 2, right? Then both sides we can divide by r power n minus 2. Here also r power n minus 2. It will be r square equals to r power 1. This r power n minus 2, r power n minus 2 will be cancelled. So plus 2. Now we can take this thing into left side. So r square minus r minus 2 equals to 0. This is our characteristic equation. We have the recurrence relation. From recurrence relation, first we need to find the characteristic equation. Now we got the characteristic equation. Next we need to find the characteristic root. We need to solve it. So multiplication will be minus 2, addition will be minus 1. So minus 2 plus 1, right? So in place of minus r, we can write minus 2r plus r. Next from these two we can take r as common, from these two 1 as common. So after taking r common, r minus 2. Here after taking 1 common, r minus 2. So it is r minus 2, r plus 1 equals to 0. So r value can be 2 or minus 1. When there are two roots, we can apply the theorem 1. When there is one root, we will apply theorem 2, that I will discuss later. When there are multiple roots, we can apply the extended version of theorem 1. Now we got the root. Next we will write in the solution. Okay, in place of r1 we can write 2, and in place of r2 we can write minus 1. So an equals to alpha 1 2 power n plus alpha 2 minus 1 power n, and we have the initial condition a0 equals to 2, a1 equals to 7. So what we'll do, in place of this n we can write 0. a0 that equals to 2 equals to alpha 1, in place of 2 power n, 2 power 0, 2 power 0 is 1 plus alpha 2 minus 1 power 0, it is simply alpha 2. Then a1 equals to 7 equals to alpha 1 2 power 1, it is 2 plus alpha 2 minus 1 power 1, so it will be minus alpha 2. So alpha 1 plus alpha 2 equals to 2, and 2 alpha 1 minus alpha 2 equals to 7. Next we need to solve this and find alpha 1 and alpha 2 value, right? 2 alpha 1 minus alpha 2 equals to 7. Alpha 1 plus alpha 2 equals to 2. Now alpha 2 will be cancelled. So 2 plus 1, 3 alpha 1 equals to 9. So alpha 1 equals to 3. Now we find the alpha 1. Now substitute. So 3 plus alpha 2 equals to 2. Alpha 2 equals to 2 minus 3. It is minus 1. So we found alpha 1 as 3 and alpha 2 as minus 1. Now substitute alpha 1 and alpha 2 value in the solution. So after substituting, we got an equals to 3 2 power n minus 1 power n, right? So in place of alpha 2 we substitute minus 1, in place of alpha 1 we substitute 3. So this is the solution of the recurrence relation an equals to an minus 1 plus 2an minus 2. In today's lecture I discussed how we can solve linear homogeneous recurrence relation with constant coefficient. In theorem 1 we discussed how we can solve a characteristic equation having two characteristic root. In next lecture I will discuss one more example, and I will discuss theorem 2, where we can discuss if we have one characteristic root. If this lecture is helpful for you, please like, share and subscribe. Thank you.